All right, good morning, everyone. Let's get started with today's class. So today we're going to start a new project that I just uploaded a partial script to GitHub. So I do ask you to, if you want to first do a Git pull on the 2024 DSA, so you get the latest script. And after that, I want to ask you to start a new project or a new repository on your personal GitHub that's going to be called 10_multivar, like you're seeing on my side. So if you remember, you start that on your side, you make that public, you add a git ignore for R, and you add a README, and then you create that repo on GitHub. You copy that address from GitHub, and then you come on your computer, you launch in your Studio window, start a new project, version control, paste that GitHub repo that you just created or the address for that, and then browse to the main folder of this course, which would be, should see like all of your previous projects. And then you create the new project there. That is going to create the folder for you, already create the rproj and the README. At that point, you're gonna have to create the code, data, and output folders. And then I wanna ask you to do two things. One is to copy the new code that I just shared with you inside of the code folder here of this new project. And the other one is on the data. I want you to navigate to the previous project, so the 09 open data. On that data folder, we had the last thing that we did was to export all the weather summarized data feature engineered with the name weather_month sum. That is the data set that you want to copy from that 09 open data project and paste inside of the data folder of the 10_multivar. So in the end, it should look like this, where you have the 10_multivar that you created from GitHub, brought it over, should get, you should have under the code folder your partial script. You should have under the data folder the weather month sum.csv that again we exported as part of the previous project, the 09 open data project. I'm just going to give you all a moment to do that and catch up, and then we'll get started. So the weather month sum.csv should have been exported as part of the previous project. So that should be under 09 open data on the data folder, weather month sum. So that was the last thing we did on the previous exercise. Anyone needing help or having questions, I can help out. All right, I think at least here in Athens that I can see, I think most people already caught up. I'm gonna get started, as we're gonna have a little bit of theory in the beginning and also throughout. So if by the time that we start coding, you have not been able to complete this, let me know and I'll wait a moment. But if I don't hear anything, I'll just keep moving. All right, so if you wanna, if that has not already launched on your side, you can go ahead and launch this rproj, which I'm gonna do on my side here. And I wanna launch my partial code as well, so we can start working on that. Here's my font size. Okay, so we, on the previous exercise with the feature engineering of the open source weather data, if you recall, we ended up creating 72 new columns, 72 new features related to weather. And now we want to try to start to understand if we can use those variables to predict cotton fiber strength, which is our data set that we have almost 700 side years, so almost 700 rows in that data set. So with that, we fall into this category of having a multivariate problem, because now we have many predictors or many X variables that we can use to, in some combination, in some form, to try to understand the effect on a given response variable. So before we really get into the machine learning type of exercises, we're going to first have this exercise talking about multivariate data sets and problems, some of the issues that we may encounter with those, how to remedy them, and a couple of algorithms. So one for dimensionality reduction, we're going to see principal component analysis, and another one for clustering, which in our case is going to be k-means. So really our goals of this exercise here are going to be to explore what it is and when to use multivariate analysis, explore a few different types of those multivariate analysis. Then we're going to be importing this data set into our environment and start running a few examples with it. We're going to talk about multicollinearity. It's a very important issue in statistics and data science, and we want to cover that, understand what it is, and how we can at least try to account for it. And then we're going to do a principal component analysis and also k-means for clustering in the end. So this script here, I don't think we're going to finish today. It's probably going to be worth a couple of class periods, but let's see how much we can cover today. Okay, so just before we start talking about multivariate in itself, I just want to talk about a few concepts here that are going to be important for us to be speaking the same language, make sure we understand what we mean by different names. So if we have this overall general equation that we've seen many times, we have a y variable that we're explaining with one or more x variables. So normally, especially in design experiments, it's common to have this y variable being named as either response variable or dependent variable. So that's some of the names that we see for the y variable in experimental design analysis. However, as we start talking more about machine learning, you're going to be seeing some different terms, but really mean the same thing. So one of them would be predicted variable, right? So this y variable here can be called any one of these three names. They all relate to that y variable. Similarly, on the x variable of the formula, so everything that comes on the right-hand side of that tilde, so variables that we're using to explain y, we normally call them explanatory variable and independent variable. So these are the names that we see most commonly with experimental design types of analysis. Then more in machine learning world, we see the word predictor variable. So if we think about it, y is what we're trying to predict. So it is a predicted variable. And we're doing that by using all the x variables here. So they are the predictor variables, right? So we're using the predictors to try to make a prediction on the predicted variable. So we're going to be seeing that nomenclature more as we get into the machine learning part of this content. Okay, so now that we are on the same page about how we call these variables, what makes an analysis multivariate? So most commonly, basically it's just that we're combining many variables into this analysis. Most commonly, what we see is we have multiple X variables, so multiple predictors in the form of you would have your Y being explained by X1, X2, all the way up to Xn, right? So one example for us here in ag would be trying to predict yield as our Y variable as a function of precipitation, temperatures for organic matter, hybrid, other things, right? So this would already be considered a multivariate analysis because we have many variables here on the right-hand side of the tilde. So we have multiple X variables. Sometimes that could also be the case that we still have multiple X variables, so multiple predictors, but we do not have a Y variable. We do not have an outcome. And this, we're going to see, so k-means is one example of this, and actually PCA is also an example. So principal component analysis is also an example of this, where you're basically giving a whole bunch of variables to an algorithm and asking it to give you groupings of sorts, but you're not really trying to use those groupings to explain something. So that's something that you would explain that Y variable is not there. Those algorithms are not taking a Y variable here, just giving a whole bunch of variables that will come on the right-hand side of that tilde and asking for the algorithm to come up with groupings of those variables for you. And another example here would be to have multiple variables, but then on the Y side of the equation, so on the left side. So if you've heard of MANOVA is one example of this, where you may have a couple of response variables on the left-hand side explained by many X variables here. So one example would be if you're trying to concurrently run an analysis of variance for both yield and biomass as a function of precipitation and temperature. So this, at least in my experience, is what I see the least, and we're not really going to cover this in this course, but it's just another form of multivariate that I wanted to expose you to, at least the concept of that. Okay, so when do we really use multivariate analysis, and why do we do that? So normally when we're interested in the effect that multiple predictors, multiple X variables can have on your predicted variable. So this is one example where we would be interested in running these types of analysis. Another case is, for example, when you have multiple predictors that you want to get groupings of. So in my other class, the programming precision class, we're just starting to go through management zones. So imagine that for that, if you're not familiar with it, you can have multiple variables at the field level, and then you want to find zones of that field that are alike. So you just give all these variables to an algorithm and asks it to give you back clusters of variables within that field that then you can treat similarly, you can manage similarly. So these would be clusters and clustering types of analysis, which k-means is one example of that. And these are, at least from my experience and what I see a lot in the literature, is that these types of multivariate analysis are normally not coming from design experiments. These are things that maybe it's an observational study that you collected a whole bunch of samples from many environments that don't really have a design component. It's not like you were not really randomizing and replicating things. You were just going out collecting samples that perhaps they did have some structure. Perhaps you sampled 10 fields, and for each field you pulled, I don't know, 20 samples. So maybe they have some structure, but that wasn't necessarily designed in a way of randomizing and replicating. So it we tending more towards the side of observational types of analysis. All right, so multivariate analysis can be of different types, and each different type would have a different purpose. So one of the most common ones that you're going to see, and especially important in data science, is for dimensionality reduction. This is very important when you have many variables in the sense of many predictor variables in your data set. And perhaps you don't want to use all of them because they are you have variables that are correlated, and we're going to see in a moment here how that can be an issue. Maybe you don't want to use, if you think of like perhaps if you have hyperspectral sensing data, where maybe you're getting, I don't know, let's say 200 bands on the sensor. So one scan of a leaf gives you 200 columns that you can then create many more columns, many more vegetation indices out of that. So let's say we end up with 500 columns that you can use to predict something. That's a lot of data, right? It's really a lot of data that there is probably a lot of correlation in the data set, meaning that perhaps you don't need to have all those 500 columns to make a good prediction about something. So principal component analysis is one way that we can extract the most important relationships of the data sets and really only use perhaps a handful of features rather than 500. So that is one very common example. There are other types of dimensionality reduction techniques like principal coordinate analysis or factor analysis. They all share commonalities. Of course, they're different because they exist, they have different names, they do things slightly different, but they all share this commonality of trying to understand a higher complexity of your data set and simplifying that to only a few features or maybe a handful of features rather than hundreds of features. Another type and also purpose of multivariate analysis would be for clustering. So again, if you have all these variables that you believe have some commonality between them or among them, and you want to create groups that are alike, or you want to group observations that are alike in distinct groups. I guess that's a better way of saying this. So we would be creating clusters, right? So one, maybe the most popular clustering algorithm is k-means, which we're going to see more, we're going to talk more about that today, or during this exercise here, perhaps not today. But some other examples here would be c-means or x-means. So these are all distance-based algorithms that basically are calculating a distance between two observations. So some sort of distance and using that to assign commonality or similarity between those observations. Another type here that you may see is non-numerical multidimensional scaling. This is it's a different algorithm. It works differently than the k-means or the means type of algorithms. And it's also another option here. We're going to talk a little bit more about different types of clustering algorithms and some of the pros and cons. We're not going to run an example on that, but it's just wanted to list that here. And another example of clustering would be nearest neighbor. So the same concept of using distance of neighboring observations and trying to come up with groups of observations that are similar. Another example here would be, so, if we just take a step back. So the main types of multivariate and the main goals that they fulfill. So dimensionality reduction is the first one, clustering is the second one, and the third one is assessing relationship between variables and or making a prediction. So this would be cases where you do want to establish a relationship, because up until here, so dimensionality reduction and clustering don't really establish a relationship. They basically just group things that are similar in reduced dimension. However, we normally want to create or establish these relationships, especially for making prediction in a machine learning setup. So this would be, types of analysis that we do that. So we would have a y variable, we would have a predicted variable, and then we have many x variables that are trying to make a prediction on that y variable. So these would be things like multiple linear regression, stepwise regression. So these are techniques that we're not going to necessarily go through them in this class. They are on the simpler side of things, but they're also very useful for establishing these relationships. And then we're going to go through random forest and conditional inference tree models that help us to establish that relationship and that predictability of models. And these are all multivariate examples. Okay, so if we think about it, there are a few different ways that we can characterize these types of algorithms. So one of them would be based on the goal of the analysis. So, for example, if you want to decrease the number of dimensions, you would use one type of multivariate analysis. If you want to create clusters, would yet be a second type of analysis. And then if you want establish relationships and make predictions, it's going to be a third type of analysis. All these types of analysis are different algorithms that are working differently behind the scenes to fulfill that objective. So we just talked about these three above in a little bit more detail. However, we can also categorize these algorithms depending on the Y variable, so the outcome, the predicted variable, and how that model incorporates or not. So for example, if you have a Y variable, if that algorithm accepts a formula of the type Y to the X, where you do have a Y variable there, it is called a supervised algorithm, meaning that you're given it the answer, which is your predicted values. So you're given the Y, you're given the yield, you're given the strength of the fiber, and you're asking for it to establish relationships of the X variables in explaining that Y variable. So you're given in the label. You're going to hear this word of label a lot. So label just means you're given the answer to the algorithm, and you're asking for it to learn the paths of to go from your X variables to making a prediction or understanding your Y variable. So if your model has a Y on the formula, it is supervised. However, if that model does not have a Y variable on this formula, it is unsupervised. So unsupervised is almost like when you don't have the labels or you don't know the labels, right? So the management zone example is a good example where you may give the algorithm elevation, soil nutrients, soil texture, other soil-related variables, and you're asking for it to create groups that are similar. You don't know how many groups there are. You just say, give me some groups, and then it's going to do that for you without trying to explain something. There is no Y in that formula. You're not saying, give me groups that explain yield. You're just saying, give me groups based on all these variables. So in that case, it is unsupervised. When you do not have a Y variable, when you do not have labels, you're actually, normally when we use unsupervised, we actually use that because we want the algorithm to create labels for you. And you may not even know what those would be beforehand. And we're going to see again one example of this later in this exercise. Now, if it is a supervised analysis, so if Y exists, then we can also classify that algorithm on what it is doing with the Y variable. So if the Y variable is categorical, this algorithm would be doing classification. So for example, let's say that, let me try to find like a quick, easy example here. So let's say that maybe I do have a numerical variable like yield, but I classify that variable into high, medium, and low yield. So now instead of having a number, I have classes, right? So I have high, low, and medium. And that column saying high, low, and medium is what I'm giving as my Y variable. So now I'm trying to say, classify all these environments based on all these X variables that could be soil, weather, management, genetics, whatever it is. And I want you to be able to make a classification using these variables and make a prediction if that environment is high, medium, or low yielding. So not an actual number of yield, but just a class of yield. So that would be a classification exercise. And then coming from that example as well, if a Y does exist and it is numerical, so if instead of giving that class of high, medium, and low, you actually give the numerical value of yield, then there's going to be a regression type of analysis. And some of these algorithms, for example, random forest, can do both. It just depends on what is your Y variable, if it is a categorical or a numerical variable. Random forest can do both a classification approach if your Y is categorical, or a regression approach if your Y is numerical. So this would be I guess, the three different categories of how we you can think of and classify these algorithms. So based on the analysis goal, based on whether or not it has an Y variable, an outcome variable on that formula, and if it does, if that Y variable is either categorical or numerical. Any questions? Yes.
When they will make a cluster, they will make similar kind of variables on the data. When they're doing a cluster, they are making similar kind of variables. Then what about the collinearity? When they will be similar.
So when you say similar, you mean correlated? Yeah.
I don't distinguish the difference. I mean, when there will be similar type of variables, there will be multicollinearity.
That's right.
Then why we are doing the cluster?
So the cluster, so if the really when we think of multicollinearity issues is mostly on a linear model type of situation where we're combining multiple variables in a formula to explain something else. When we are creating clusters, that's actually it's a really great question, and I don't think I read or ran into that issue on my experience as far as because when we're clustering, we will most likely be using collinear variables. Yeah, I guess I don't have a good answer for you there. It's something that we can actually try with this data because we definitely have multicollinearity issues on this data, and we're going to do k-means. So maybe we can try. Well, I'll give you some ideas when we get to that point, but it's something that we can actually try. So I guess to answer what you're saying, I have not had issues of evidence of multicollinearity causing issues for clustering, but I also have not explored that in much depth. So maybe that could be an issue and I'm just not fully aware of it, but we can try that here with this data and see if that makes a difference or not. My intuition is that multicollinearity is not such an issue when you are clustering because we're using Euclidean distance, or we're using a measure of distance between the variables and not necessarily like a regression approach, which is where we see multicollinearity issues more frequently. I could be wrong, but we can check on that. Yeah.
Otherwise, why there is no issue, but I don't understand why there is no issue.
Yeah. Well, let's do this. Let's try to do that when we get there and see if there's a difference, and then we can, start thinking about that problem together. My intuition is that on clustering, I don't expect to have such an issue of even though multicollinearity is going to be present, but I don't think it's impacting much of your results because we're using a distance from points as our way of creating clusters and finding similarities, which is not what we do with linear regression, right? Linear regression is not distance-based. It is a different approach. And that's where normally we see multicollinearity issues. So that's my intuition going to it based on what I've seen and what I've done, but we can check that when we get there. And I hope, and we're going to have a multicollinearity exercise in this script. So at that point, maybe that's going to also help us to create this intuition of what that is and how that impacts, especially linear regression. And then when we get to the k-means, we can do some tests and see if that impacts our goal. Thanks, Neva. Any other questions? Yes.
Could you explain further what you said about the principal analysis or what is that? Because I think that k-means is very different.
So we are actually going to have a more in-depth conversation and application of principal component analysis in this script here. So I think if we just pin that until we get to that point, I think that's going to clarify. And if it doesn't, then we can follow up at that point. But yeah, for now, so the goal of this script here is first, we're going to do some EDA, exploratory data analysis as always. And then we're going to talk about multicollinearity. We're going to see an example of that in practice and how that may impact our models. And then we're going to get into PCA and then K-means. So when we get to PCA and K-means, then we're going to see some more examples and explanations of that. And if that is not clear at that point, then definitely please ask again and we can talk about it. Okay, so the first chunk that I have here for us is just loading some packages. I do not think I had asked you to install these 3 packages before. So in case you don't have them, which you can check by just trying to run the library function. So for example, the GG core plot, if you just run that library function and it says you don't have that package, then you have to install it. So I left you here the code to install all those 3 packages. As you already know, just uncomment the line that you want to install, run only that line, don't run the whole chunk. And then once that goes through and install, you can either delete this line or just comment it off as well. And just do that, for the 3 packages here, have them installed as we're starting this exercise. All right, so go ahead and load this or run this chunk after you install the packages. So we load all those packages. And the first thing we're going to do here is actually import our data. So if you remember, I just asked you to copy that data set, weather month sum.csv from the previous project into the code folder, or I'm sorry, into the data folder of this current project. So let's just read that. Let's call it read_CSV. So open quotation marks, we do .. to get outside of the code folder. We navigate to the data folder and it should be the only data set there. So if you read it in and you just printed a quick recap here, we've seen this data already before, but we have 698 rows because that's how many site years we have in this data set. Excuse me. Where the first column here is year, the second one is site. And then we have our Y variable, our predicted variable of strength in grams per tex. And then all of our X variables, our predictor variables that are the summaries of the different weather variables in different months for each one of the site years that we created previously. So we have 72 predictor variables and 1 predicted variable in this data set. Okay, so one thing that is going to set us off to understand multicollinearity is first understand what if these variables are related or correlated, and if there are any strong correlations in this data set. So for that, I want to create a correlation matrix. So you may have seen this where basically my goal is to have all these variables on the x-axis, all these variables on the y-axis, and have this matrix of correlation that are going to be colored depending on the strength of that correlation. So we can have a visual assessment of that. So the first thing that we want to do here is I want to calculate the p-value of those correlations because I'm going to use this in the plot itself. So we're just going to do that first in this first chunk. I want to call that p.mat. Just give it the assignment symbol. We're going to start off with the data set we just imported. So that's weather. I do want to remove year and site because year, even though it's numerical, but I don't really care about the correlation of year with other things. And also site is not going to really make a lot of sense. So let's just select out using dplyr select minus year, comma, minus site. So if we just run this, that is basically weather with 2 last columns. So we just keep strength and then all of the predictor variables. And now give it a pipe, and we're going to call this function called core_pmat. So this function is coming from the GG core plot package, the one that we just installed. So if you run this, this is basically just a matrix or an array of data with the p-value of the correlation of all 72 by 7, all 72 variables, but by the same 72 variables. So this in itself is really not that useful. I mean, if you just want to close this output window here, because it's going to be a long output, you can just close that window right there on the X. But I just wanted to show you that this is just the PMAT, just holds all the p-values of the correlation among all these variables. Now, the next thing is for us to create a plot. I left you here all this code because, you know what, I'm just gonna walk you through what this code is doing. So we're starting with weather, piping that on a select and leaving ear and side behind, and piping that into this core function. So this core function is for correlation. And just as a reminder, we have R and we have R squared. This is giving us R. So it's that correlation coefficient that can range from -1 to 1. This is what is given us. It's just a matrix with those correlation coefficients ranging from 1 to -1. And then we just plug that right into this function GG core plot, and I'm just changing some of the arguments here just to control how that looks like. So I'm asking it to order the variables based on their correlation, to only have one digit on the R value on the plot, to only use the lower side of the correlation matrix that's going to show us, to use the PMAT that we just created, and if that significance level is greater than our alpha, then it just doesn't even show it, so it hides that away to make it a little bit simpler. And then if it is non-significant, it makes that cell blank and adds labels. If you run this, it's going to be kind of a big correlation matrix that, at least in R, is kind of difficult to see. So I left you here the code to export that to file. So if you do run that ggSave, perhaps it's a little bit, still going to be difficult because we have a lot of variables, but if you go on the output folder, we're going to be able to see that file. I think it helps a little bit to see what is going on, because then we can zoom in and out as well. So here, what it's doing is it placed all of the 72 variables, or 73 variables, I think, on the x-axis, the same variables in the same order on the y-axis. And then we have this matrix of correlation where the diagonal here, let's see. No, this diagonal is actually not what I was going to say. But so what we have also in these cells is the actual R value of that correlation. So again, R ranges from -1 to 1. So we see this number right inside of the cells. And then the cells are also colored by that correlation itself. So if it is a positive correlation, it is colored in red, and the darker red it is, the stronger is that correlation. If it is a negative correlation, then it's colored in blue, and the darker blue it is, the stronger is that correlation. And if something is poorly correlated, the color is closer to white. And if it was insignificant with alpha 0.05, then the cell just doesn't even appear. So this is a correlation matrix here. Again, it's a little bit difficult to really see because there are so many variables, but we can kind of see there is a grouping of negatively correlated variables right here. If we were to just inspect those, if we project that on the x-axis, those are related to mean day length in September, August, July, June, April, and May. And then if we project that on the y-axis, these are going to be mean day length in January, February, or Tmax in January, day length in February, January, and October. So we see that there are some strongly negatively correlated variables, some strongly positively correlated variables as well. We see the red ones right there, and then a lot of mix in between. Again, if you have less variables, this matrix is more helpful because you don't have so many numbers and cells on this matrix. You can always still, include something like this in a paper or a supplementary figure if you wish, because it is perhaps one of the easiest and most intuitive ways of assessing all these correlations in one place. All right, so we did see that there are some variables that are highly strongly correlated. But then I also left you here some code for us to look into those values on a table format, because then we can do, it's easier for us to really see what the number is, what those variables are. I left you the code as well. Let me walk you through what is going on here. So we're starting with weather, removing year and site, and plugging that into that core function. So the same that we use for the plot, which gives us the R value of all. So if you see here, we have each column is one of the variables, and then each row, in this case, these are row names. Each one of the row names is, again, one of those variables. This output is very long because we have such a large matrix. But then I am transforming the output of core into a data frame. So let me run into there so you can see what happens. So this becomes a data frame, so a little bit easier for us to manipulate it. Still, we have the variables here. The first time they're appearing is as row names, and then they're appearing again as column names. So if I do want to have these row names as an actual column in this data set, we use this function called row names to column, which is basically just going to bring those row names as a column that now is called row name. And then the way that we would see this is basically, so the strength here, when it's correlated with strength itself, correlation is 1 because it is the same variable. And then strength correlated to, each variable that you go to the side here is going to be a different correlation between this row, which is always going to be strength for the first row, and each one of the columns. However, I do want to pivot this longer, where I just want to basically pivot longer all the other columns except row name. So I have another column saying name, which is going to be all the current titles, and another column called value, which is going to have all the values for now. So let me do that until here so you can see how that looks like. So now basically I have these pairs of this variable, and this is that correlation, right? So I have all these in just 3 columns. I do want to filter only correlations that on an absolute value are greater than 0.85, just to make this easier for us to extract the highest correlations. Because this value here, so the column value can range from -1 to 1, and I want to filter both correlations that are greater than 0.85, but also lower than negative 0.85. So it goes on both sides. There's a couple ways we could do that. One of them is just to ask for the absolute value of that column value. So this basically turns everything into a positive number, and then I can just filter that positive number being greater than 0.85, and except for the ones equal to 1, because that's just the variable by itself, right? Or the correlation of that variable with itself. So I don't care for those, but I do want everything that on absolute terms is greater than 85. And then I'm just arranging them in descending order. And if I run until here, just so you can see, I have repeated pairs. So when mean day length in January and mean day length of December, they have a 0.99 R value, correlation value, but then the next row is the same combination, but just with December appearing first and January appearing second, it's the same. So everything is duplicated because of that, because of the matrix. So I'm just getting a distinct, getting only the distinct values of this column value here, so we don't have those repeated cases. So when we do that, we see that the greatest correlation we're seeing here is between mean day length in January and mean day length in December, with a correlation value of 0.99. So very highly correlated. This would be a multicollinearity issue for sure. And then we just see how all of these variables in descending order, the highest correlated ones, which pairs of variables created that correlation and what that correlation was in fact. So this would be one way that we could explore this in a little bit more manageable way, rather than looking at that very complex, large plot that we just created. Now, if I wanted to assess some of the least correlated variables, I could do the same thing. So if you go to the next chunk, we're doing the exact same thing. The only difference is on the filter. Now I'm filtering the absolute values that are less than 0.05 in terms of that R value. So that's the only difference of this chunk. If you just run that, we see here, for example, that the least correlated variables in this data set or pair of variables was the mean day length in April and the cumulative precipitation in October with a very low R value. So very little correlation between those two columns. So this is just, again, a way for us to have some understanding of, okay, do we have variables that are highly correlated in this data set? Yes. Which ones were they? We explore on the chunk above. And then also I wanted to show you a way to get the least correlated ones in this data set and how to find them. So this would be how you would do that. I guess any questions until this point? All right, I don't hear anything, so let's keep moving. Another question that I have, so right here, if you were to look into the plot that we created, let me just open that plot again to show you. Strength was one of the rows and columns in that plot. So let's see, where is strength? Oh, right here. So strength is one of those variables here. So let's say if I really wanted to only see the correlation of everything with strength, I could have just come to this column here and just go up this column and assess its values. However, again, doing this with these many variables is a little bit difficult to make sense. So what I want to do is understand that correlation of all these variables with strength, which is our predicted variable. So the one that we're really interested in seeing what types of correlations we have. I wanted to visualize that with some plots. So if you come after that chunk that we just did with the lowest correlations, if you go after that chunk, there's a chunk that I also left you a lot of the code in there. So what I'm doing here, and again, I'm leaving you this code because we have done these steps before, and I don't want us to just, spend a lot of time in something that you already learned the concept. So I'm starting with weather, selecting outside and near, pivoting longer all the variables except for strength. So this is how that's going to look like. So I still have strength repeating for all of the different predictor variables that are now under this column called name. I am grouping by name and nesting in a way that this is how it looks like. So for each one of the predictor variables, I have a data frame that has both strength and that variable itself. Then I'm piping that into a mutate with a map DBL. So this perhaps is the newer thing right here is we've used map before, and I could have used map here as well. But because what I'm looking for is just a number, which is the R square of that correlation, of that relationship of strength in each one of the variables. So my outcome, which is R square, is just a number, it's just double. So I can use the map underscore double to control the format of my outputs. So in this case here, I'm getting each one of those data cells in this column here, and then doing this where I have strength as my Y variable on a linear model, and the value, which represents each one of these columns here for each one of those data sets as our X variable. The data here equals .x because that's what is coming through the map. I'm using this function called glance, which basically creates for us a whole bunch of metrics of this model here, including the R square. And then I'm pulling just the R square from this output of glance. And this is just a number then, which gets into that column called R square. And then I'm just arranging from highest to lowest R square. So if you just run this, we basically have those columns, we have the data, and then we also have the R square of each one of those variables and their relation, their bivariate relationship with strength. As we can see here, R squares do not look very good. I guess one difference just to note is that this value of R square, this is R square already. What we were seeing up until here was R, right? So to go from R to R square, you can just give a power of 2 to this number, that would give you R squared. So we're seeing that, well, and also, let me just make the other distinction here, is that these values are all, like, you know, they have all the predictor variables, and strength is also here in the mix. But in this case here, we're explaining strength itself with those values. So it's not everything against everything. Now it's just everything against strength only. And then we're getting the R squared. So we see here that really does not seem that on a bivariate relationship, we would be able to create very strong predictive models with this data set, because the largest R square we're getting is 0.065 with mean solar radiation in April. So that is our best predictor, but it's still a very poor predictor overall because the relationship between that and strength is very weak. Now, if I wanted to, so this is just R squared itself, but what if I wanted to create scatter plots of strength and perhaps the top 6 variables here? So not all 72, because that would be too many plots again, but I wanted to take the best top 6 variables and do this scatter plot of these relationships so I can actually visualize. That is something I completely, totally encourage you to do. Is these tables are useful for us to quickly get an answer and a very objective answer, because we have the R square right there. But even then, always make sure you plot these, because you will be amazed by how many times, if you don't plot things, don't see what's going on, you may be creating a wrong intuition. And I actually, let me write a note here, because I want to send you all an exercise. Have you all heard of the, I think it's called Statosaurus data set? It's a very, very cool exercise that basically has, it's an overall data set that in itself, it has, I think, like 10 different types of data sets where they all have different shapes when you do a scatter plot of 2 variables. But even though they're very distinct shapes of the data, they all have the same R squared, the same p-value, the same, a lot of similar metrics when it comes to correlation. Now, let me see if maybe I can find that, and then Statosaurus R squared. Let's see, maybe that's it. No, okay. I'll look for that and then just send a link for you all to see this. But basically, it's this concept that, so one of the data frames is just a scatter plot that you would normally expect, like, you know, like a positive relationship. One is in the shape of a star, one is in the shape of a dinosaur. That's why it gets its name. And when you do a scatter plot, they're all very different, but they all have the same intercept, slope, R squared, and so on. So just making the point of always plotting things so you see what's going on and not just relying on numbers, which is what I want to do in the next step here. So I also left you all the code, which is the same up until here as on the previous chunk, but then I am ungrouping, I'm getting the top 6 models, I am unmasking the data, so it goes back to a very, so let me run until this point so we can see what is happening. I'm getting just the top 6 models here, the highest R square ones. I am unmasking the data, so I get all the data back from those 5 data frames. So now I have 4,000 rows, and then I'm putting that on a ggplot and faceting by the variable name. So I get one scatter plot of a given variable versus strength, and I can see that relationship. So this is how the best 6 models look like when explaining strength. We see here that there's a lot of noise around that regression line, and this is probably what's causing our R-squared values to be very low. We do see that, there is a relationship here, especially for the first 4 plots. So solar radiation in different months is negatively associated with strength. And then vapor pressure and precipitation in April are positively correlated with strength, cotton fiber strength. So again, just getting some plots here, visualizing this relationship, understanding what's going on here. Okay, before we start talking about multicollinearity, any questions until this point? So notice that up until now, this is all exploratory data analysis, right? It's just us creating a sense of how these variables relate to each other and how they relate to strength, and kind of creating this understanding, checking our data, creating some hypothesis perhaps. Okay, so let's talk about multicollinearity. So the definition of that is whenever more than 2 explanatory variables, so the X variables on your formula, in a multiple regression model are highly linearly related. Whenever that happens, so if you have a model, in our case, let's say we would create a multivariate regression model. So imagine we had strength, cotton strength as our Y variable, and then all the 72 weather variables on the right-hand side of the formula. As we already saw on the correlation matrix and on the tables that we did, we have many variables, many weather variables that are highly correlated among themselves. That would create a multicollinearity issue. So whenever that happens, the implications of that is that our model estimates, so let's say, the slope or the intercept of the regression, both the magnitude of that, so let's say, if the slope is maybe 1 for something in a regression that is known multicollinear, if you have the same variable in another model that has multicollinear variables with it, now its slope may be -10. So we may change not just the magnitude from 1 to 10, but also the direction of that relationship from 1 to -10. So this is one of the effects of multicollinearity, which really messes up our interpretation of those effects, right? So if you run a model, let's say, strength explained by, I don't know, day length in January, and the relationship is positive. Now, if you add the day length of February, which is highly multicollinear with the day length in January, now maybe January has a different effect. So if before by itself was a negative relationship with strength, now in a model that is multicollinear with day length in February, it may be a positive relationship. So it may change the way that we interpret these variables in these models, which causes issues for us, because a lot of times we want to understand, we don't want, I guess we can talk more about this in future classes, but normally, at least my goal is to create predictive models that I can interpret and not just a black box. So if you're trying to interpret something and you have multicollinearity issues, then your interpretation may be completely misled by that. Not only changing the estimates, but also the standard errors around that estimate. This is something that multicollinearity also does, is inflates your standard errors around those estimates, which will impact your p-values, the estimate significance, and the power of your analysis. So multicollinearity is a real issue that we need to be aware of and trying to find ways to remedy it whenever possible. All right, so I do want to show you an applied example of multicollinearity with the data set we have right in front of us. So the first thing that I want to do here is I went up to the chunks where we had the highest and lowest correlation. So let's see, I think here on the highest, I think day length in April and in May were very highly correlated from that table. Let's see if I come here, day length I know they're somewhere in the top highly correlated variables with an R square above, or with an R value above 0.99. If I just come back here to my plot, so I'm plotting, I'm sorry, uncorrelated first. So the uncorrelated had a very low R square on the lowest R square chunk. So mean day length in April and cumulative precipitation in October. If you run that chunk, I left the code for you already. I'm just putting one on the X, one on the Y, getting a geom point, so we get a scatter plot, doing a geom smooth, so we get a linear model for that, and also just using this function stat correlation, so it plots for us the R value. As we can see, the R value here is very low, and on the scatter plot, we can also notice how that relationship is very insignificant, right? We see that the slope is basically flat, meaning that there's no relationship here as you increase your day length in April, that has no effect on the cumulative precipitation in October, which, you know, I'm not a meteorologist. My gosh, I'm getting this word wrong. I don't work with weather data enough. I don't get a degree in weather data. So, but from my intuition, I would not expect for these two variables to be correlated anyways, right? So this would be an example where we have two variables in a model that are uncorrelated. If you go to the next chunk here, I got two variables that are highly correlated, and that was mean day length in April and mean day length in May. If you plot them, you see that this correlation is very strong. I guess I forgot to add here the stat. Let's see, stat correlation. So it actually plots for us. You can just go ahead and add that stat underscore correlation. That's gonna add for us the R square, which is the R value, not the R square, which is 0.99 in this case. So building from this, I just want us to remember here, day length in April and in May are highly correlated. But right now, there's no multicollinearity issue here because this is just a bivariate model. Multicollinearity issues happen when you have multiple X variables that are correlated. Your X and your Y variable may be correlated, and a lot of times we want them to be correlated because we're trying to explain one with the other. So multicollinearity is not about Y and X, it's about many X's. So right now, in this example, we just have one X variable. So multicollinearity is not even something that would play a role here or here, right? Or on the uncorrelated example. So now what I want to do next is run these models that I just showed the scatter plots of by themselves, and then run again by adding a correlated variable with one of them and an uncorrelated variable with them, and see how that impacts the estimates that we get out of these models. So if you come here on the next chunk, we're actually going to fit those models, and you're going to help me here with the coding of that. Let me pull up my cheat sheet here. So the first case here, I want to plot strength as a function of mean day length in April. So you can come on this object that I left you here. Let's give it the assignment symbol. We're going to call the function lm, which we use for, simpler linear regression models. If you remember, what we're going to give it is y to the x, where y is strength in grams per tex. And then our x variable is, if you just want to copy this from above, I think it's going to make your life easier. So mean day length dot s underscore APR. And then we need to give it the data where that's coming from. So we give it a tilde. I want to break code just to make it easier to read and say data equals weather. If we just run this, we're basically running this linear model, which is a regression. And we know it's a regression, it's not an ANOVA, because we have two numerical variables, right? If the variable x here would have been categorical, this would have become an analysis of variance. Because they're both numerical, this is a regression. So if we just print that object, it's just giving us an intercept and a slope estimate of that relationship. So the next thing I want to give it here is give it a pipe and call for the function tidy. So the function tidy comes from the broom package and basically just creates a table, a summary table of this model that contains the column called term, where it has the intercept and the slope. It has the estimate, standard error, the statistic, and the p-value for us. I'm doing this because I'm really interested in that, especially on the slope here, because it's the slope between the relationship of day length in April and fiber strength. So I do only want to keep this row here, so do not care for the intercept at this point. So let's add a pipe. I want to do a filter where term is different than intercept. And just so you make sure you get it right, the way that intercept is written here is with a quote, it's with the parentheses. So make sure you give that correctly. So I want the term different than intercept. So I only get the slope. And then I want to create a column here on this data set to identify which data, or I'm sorry, not data set, on this model fit that we turn into a data set to identify which model this was. So I want to give it a pipe. I want to call it mutate. And I want to say mod equals to, and I'm going to give it a name, which is basically going to be the name of the object itself in quotation marks. Just so for our future reference, when we're making a plot, and the next chunk here, we know which model this is referring to. So if you run this and you print it, you only have the slope here. The term is only the slope. We have an estimate of that slope, a standard error of that slope. And then we have a name of this model, which is called LM day length in April. All right. So on the next chunk here, we're going to do a very similar thing, but with a different variable. So what I want to do is come on the next chunk and run a model where I'm explaining strength, fiber strength with the cumulative precipitation in October. I'm doing very similar to what we did before. The only difference is now we're giving the mod name is a different mod name as we did on the previous chunk. So if you just run that and just print LM pure P October, we just have this term here again is the slope. It just has a different name because of the variable that we change on the model. And then it has, of course, different estimates and error and all that, and then a different name of the model as well. Okay, so now things are going to start getting interesting. So I ran individually strength explained by, let me just show you again. So the first model we did was strength explained by mean day length in April by itself. The second model I did was strength explained by cumulative precipitation in October by itself. So right now, these models, multicollinearity concept doesn't even apply to them because we only have one X variable. Now I want to do two more models. One where I add a second variable on the X side of the formula that is going to be uncorrelated with the one that was already there. So we're going to have a model with two X variables that are uncorrelated. And then the next chunk is going to be another model with two X variables that are correlated. And we're going to be extracting the estimates and also the standard errors of these parameters of the model. And if you remember, in the multicollinear case, what happens is that our the magnitude and the direction of our estimates can change from a model where you have a variable that is not in multicollinearity with another one compared to a model where it is. And also our standard errors get inflated on a multicollinear model compared to a non-multicollinear model. So if you come here on the next chunk, I'm still explaining strength. So strength is our predicted variable using the mean day length in April and the cumulative precipitation in October, which these two variables are not correlated as we observed on some of the chunks above. So if you run that, I am calling this model here LM2var uncore. So we remember that this model here, it has two X variables that are not correlated. So multicollinearity is not a problem here. If you print it now, we have two values for slope, one for mean day length, one for precipitation, cumulative precipitation in October. So we have two estimates here, two standard errors and so on. And now, finally, and lastly, is our correlated model that we will expect to have multicollinearity problems, where we're explaining still strength. So the Y variable has remained the same across all these models, with the effect of mean day length in April and mean day length in May, which are strongly correlated, as we would have seen in the chunks on the EDA that we did. So changing the model now to a highly correlated X variable model, and just the name of this model is going to be LM2var core to mean that they are correlated. So if you run that and you print it, we have both of our slopes again. We have different estimates for each one of the variables, standard errors, and so on. So I did all this because I wanted to compare all these four models. So just to remind you here, the first model that we ran had only day length in April. The second one that we did only had precipitation in October. The third one we did had day length in April and precipitation in October, which are not correlated, as we saw on the EDA. And the last model has mean day length in April with day length in May, which are extremely correlated. So what we would expect is, especially because these models are just the main effects, they're not including interactions, you would expect that the effect of mean day length in April for the estimate of that model to be very similar across all these models, because you are having it either alone or in conjunction with another variable. So our hypothesis here is that the effect of mean day length in April on strength, on fiber strength, would be very similar regardless if you have more variables in the model or not. Now let's see if that really happened. So if you come here on this next chunk, I just want to show you, I left you already a lot of the code here again because I did not want you to worry about it. But I'm starting with the first model fit, or the first model summary that we created, LM day length in April, which is just this. I am binding the rows of all the other three models we ran above. So if I just stop right here, we have a table with six rows here. So these are all the different intercepts for different models, their estimates, their standard deviation, or standard error, their p-values, and then the name of the model they're coming from. I am just changing the levels of those models, so the way that they appear on the x-axis of ggplots follow this order, because it's a more logical order for us to look into. I am removing the term mean day length in May, because that term is coming from the uncorrelated model. Let me show you here. So mean day length in April, or sorry, let me see. Let me make sure I tell you correctly. So mean day length in May is coming from the correlated model, actually. Right here, but it's a variable that only appears in these models. For comparison purposes and to make the point I'm trying to make, I'm just going to remove it from the plot and just look into the effect of mean day length in April and how that estimate and standard error change depending if it is alone by itself or in a model with a non-correlated variable or in a model with a correlated variable. That's my goal that I want to show you here on the next chunk. So I'm keeping that, bringing that one out, and then starting a ggplot here. I want to ask you for help for us to complete this ggplot. So what I want to do here is, I don't think we've used this next geom yet, but it's called, if you just add a plus here, it's called geom_point range, which is basically a geom that is you're gonna tell it where the point is and what the range of the error around that point is as well. So let's call here the AES function inside of it. Our Y variable, Y column here. If I just, let me just print until here so you see what the data set looks like coming in. So the Y variable is going to be equals to the estimate column. So I want to put the actual estimate on the Y-axis. And then the other AES arguments we're going to change for this geom in specific. One of them is called Y min, which is the minimum threshold of the range on this point range. So imagine that point range is going to put a point and error bars around it. So I need to say what is the minimum level of that bar on the lower side of it. So this is basically going to be our estimate minus our std.error. And then similarly, we need to say where is the upper side of that interval is going to end. So that's going to be ymax is the name of the argument. So ymax equals to estimate plus std.error. And those are columns in our data set. If we just run that, you're going to see something like this. I do want to make a few changes here for it to be a little bit easier for us to understand. So one of the changes I want to make is add a facet. So I want to facet by the different terms here. So let's add a plus and do a facet underscore rep, where I say tilde term, where the term is going to be the different slope values. And I want to say scales equals to free underscore y. So the y scale is allowed to change. If we do this, that's what we see. Lastly, I just want to make these labels here to appear a little bit more in a nicer way. There may be a couple different ways to do that. One of them is if you just add a plus, we're going to call the function scale underscore x underscore discrete. So we're going to play around with the x-axis here. And I want to say it has an argument called guide. I want to say guide equals to, and then there's a function called guide underscore axis that has an argument called n dodge. So the number of times you want to dodge, I want to say dodge n dodge equals 2. So if you run that, it basically takes like each one of the model's labels on the x-axis that were previously overlapping. So let me maybe squeeze this so we can see both together. Yeah. Well, anyways, if you still need to catch up with the code, let me know. You need, okay, let me, yeah, so this is how the code looks like. So it's basically just if you have overlapping x-axis labels, it's just dodging them. So one on top, one on bottom, top, bottom, top, bottom. That's what this part of the code is doing. It's just helping us to avoid overlapping x-axis text. So this is the product of that. Okay. So just so let's walk through this a little bit. You know, with I guess paying attention on what's going on. So we create this intuition. So this is multicollinearity at play. So here we have the estimate, which in this case is the slope of each one of these terms here. So the mean day length in April and the sum of the precipitation in October. These are the terms that I'm showing you the slopes for. And then we have 4 different models here, all the models that we ran. So if you notice here, the first model, if you were to go back to the code, this model was just strength being explained by day length in April alone. The estimate is barely above 0 and has a very low error. Then the second model that I had was strength explained by precipitation in October. So I have no estimate for mean day length in April because that was not part of that model. So there's no estimate for that. Then I had a third model where I had day length and some precipitation both as part of this model, and day length in April and precipitation are not correlated, meaning that the standard error for, in this case, mean day length in April, both the standard error and the estimate are still very similar to the standard error and estimate of the model where day length in April was by itself. Right, so on a model with two X variables where they are uncorrelated, the estimate is very similar to a model that only had day length in April by itself. Now, what happens on a model, on this last model here, where was a model that we were estimating strength as a function of mean day length in April and mean day length in May, which are highly correlated. This is the effect of that correlated model multicollinearity on the slope of mean day length as it affects strength. So if you see, this is the zero line. So first off, it flipped direction. Before it was a positive relationship. So mean day length in April had a positive effect on fiber strength on by itself or in an uncorrelated model with another X variable. But in a multicollinear model, the effect flipped. It became negative. So now mean day length in April has a negative effect on strength. And also look at the standard errors around that estimate. They really increased. So this is what multicollinearity is doing in your models. And really the problem is if you don't look at it, if you don't pay attention, you really don't know it's happening. You don't know which variables are impacting which other variables. And then as you could see here, your interpretation of these two models on the effect of day length in April on strength is completely different from this. Now probably the effect of mean day length in April on fiber strength is not changing, right? This is just the effect of multicollinearity between day length in April and day length in May, which was part of this model here. And then for the case of the sum of precipitation October, we just had a model with it by itself, which is this model here. And then we had that cumulative precipitation October as part of a uncorrelated model along with mean day length. So again, we see the effect of cumulative precipitation October not changing regardless of whether it is alone on the model or with an uncorrelated variable. But if we had run yet another model where some of precipitation October was also explained or was part of a model with another highly correlated variable with it, we would see a very similar effect on that slope on that other model, which we did not run. So really, I guess the effect of multicollinearity we're seeing on this first panel here on mean day length in April. All right, any questions about this? Yes.
I have issues with the code in the previous one. So that you would say when you first begin with the data, I have all the five additional rows. And just say here that if you do in the back place, there's a number that says EPLR, semicolon, and 5. If I do that, it doesn't work.
So if you add a pipe, so okay, let's think about this. Whenever I'm troubleshooting a pipe workflow, I like to add the comment off, like, increasingly the different pipes and just letting the code run until that pipe and see if so if you do this and you run, the code shows up, right? Already shows up?
That part that is not working, the first one.
The first part is not working, okay.
It says that in the error, it says argument 1 must be a data frame or a named atomic vector.
Okay, so it could be that maybe you did not run one of the chunks above. So what I would do is so if you just select one of them and you run and see if that prints below. So do one by one. And if you do that and it says it doesn't exist, then you did not run the chunk. Each of them. Okay, let me, I'll help you out after class and then so we can keep going here. Is anyone else having issues with this code running?
I have one small issue, Dr. Bastos.
Go ahead.
I ignored it at the time just because I didn't want to hold up class. But when I ran the exact same code for the R strength, tilde, mean date, S, and we're getting rid of the intercept column, and mine did not do that. It left it in there, and I just kept rolling on with it just because I was like, I'll come back and look at it, and I just wanted to maybe we can look at it later. But to my knowledge, I have the exact same thing. Yes, sir. It's right there. It leaves intercept in there.
Yeah, so it would probably, I mean, we can take a look at that. I would say for you to just make sure that you have a different here. So term different than, and then you have your parentheses as well as part of that string, and I is uppercase.
Yes, sir.
Okay, so if you have all that, I guess we have to look into your code. Did
Yes, sir.
anyone else have similar issues?
I think
Okay, we can definitely connect after class here and with whoever's having issues, and then we can go through that. Okay, so just to wrap up this part here, and then we'll move on. Okay, so if we base on this plot that we just saw, that we were able to see that the effect of mean day length on fiber strength changed whenever it was either alone in a model or in a model with an uncorrelated X variable, comparing that to when it was in a model with a correlated variable, X variable, right? The direction changed, the magnitude changed, and also the standard error increased when it was part of a model with a correlated X variable. So it was part of a multicollinear model. One way that we can check for the degree of multicollinearity between any two variables in the model is to use something called the variance inflation factor, or VIF. This is something you're probably going to come across as you learn more about multicollinearity. And like it's hard to give like a hard rule of what to follow, but in general terms, if you have a VIF that's around 1, then you would interpret that as no multicollinearity issues within that model. If you have a VIF value between 1 and 5, you would assume you have moderate multicollinearity. And if your VIF is greater than 5, then you have severe multicollinearity, and you're most likely making some of the interpretation of this model are being misleading because of that. So what I want to do next here is just to check the VIF of a couple of models that we already ran. So the first one being the uncorrelated model. So for that, I want to ask you that if you come here on your outline, if you're not seeing it, you just toggle that on and off. And if you click on any chunk that you can see, it's gonna show you where you are on your table of contents. You can just navigate to the I think it would be the third chunk that says strength here. So it's the one that we had the uncorrelated model. That is the LM, strength, GTAX, explained by day length in April and precipitation October. So make sure you copy that LM starting at the L and ending at the parentheses. We're just going to bring this model, which was the uncorrelated model, and then you can just navigate to the chunk that we were about to type. Just type that model again. If you run it, it's just going to be the model fit. We're not assigning this to any object. It's just printing for us on the console or below the chunk. And then we're going to pipe that into this function called VIF, which is the one we use to calculate the variance inflation factor. If you run that, it's going to give you a VIF score for each one of the X variables in this model. And we can see here that that VIF is basically 1, meaning that we have no multicollinearity issues in this model, which is something we would expect, as we already checked on the EDA part of the script, that these variables have very little correlation between them. Now, if you go to the next chunk, we're gonna do the same thing, and I left you the code already. And this is the model that had a lot of correlation between the X variables, and we had the effect coming through on the plot that we did above. So if you run this, you're gonna see that the variance inflation factor of both of those variables is very high. It's almost 65 units. So this model, as we had already expected, is very highly multicollinear, and that is impacting our estimates, our errors, our interpretation of this model. Okay, so now that I hope we were able to understand how multicollinearity plays a role in our models and how we can identify it both visually and also with this function for variance inflation factor, how do we deal with multicollinearity? How do we avoid it making issues and creating trouble in our models and in our interpretations? That's going to be something we're going to talk about next Tuesday. I think this is a good stopping point. I want to ask you to save your script and then do a git stage, or I guess if you're doing by click, come on your git tab, check all the boxes to stage all of the files that you changed, then create on that check mark to create a commit. Let's say that we finished with multicollinearity parts, and then commit, close that, and then push. All right, I do wanna, well, let me take your attendance as well, so I don't forget to do that. All right, you can claim your attendance, and I do want to briefly talk about the exam. So I have decided that the exam is going to be on your computer. There are parts of it that will allow you to make use of your scripts. So it's going to be partially open book, I guess. So make sure you bring your computer, make sure you, also, I guess, something very important is that it's going to be in person in your campus. So if you are in Athens, you come to this room. If you are in Tifton, you need to go to, I think it's NASPAL 601, the name of the room or the number of the room. If you're not sure where is your in-person location, let me know and I can help you. But if I don't hear from you all, I will assume that you are in your in-person room in your campus. If you are not in that room, you will not be allowed to take the exam. You will have all 2 hours of the next class period to complete the exam. You will submit that to me at the end of those 2 hours. And these are going to be a mixture of questions that are going to include some theory, especially what we cover in the slides. And anytime I have something written in my script, as this today was a good example, I had a lot of things written in the script as the theory and some background. So that is fair game as well, as we already talked about. I already provided you some reading material if you wanted to get a little bit deeper into the topics that we cover in class. I will not be asking you like mathematical formulas of something that we never talked about. I may ask you things that are general level but important. Like if you have a CRD with only fixed effects, what function to use? If you have a mixed effect model, I can ask you how you would specify a given model as far as the formula of that model, which is not difficult, right? It's just if it's random or not, how you specify something that's random versus something that's not random. So these types of questions are fair game, but again, my goal is not to be tricky with you, is not to, ask something that I never talked about in class that is hidden in one of the reading materials. That is not the goal. The goal is that if you're understanding the overall idea of the project, of the class, if you're following along, if you're making sense of the main topics we're covering. Any questions about either the exercise of today or the exam on Thursday? All right. So if you have no questions, I guess I'll see you all on Thursday, and make sure again, you bring your computer, bring your charger, bring some water, some snacks, if you want to, and I'll see you then.
Hey, Dr. Bastos.
I'll be right there with you, Austin. So, yes, Joseph.
That guide access code.
Oh, yeah, the guide access code. Yes, Austin.
Can we connect for a second to talk about an issue I was having with the script?
Sure, yep. If you can send me a Zoom link, I'll
Sure
be
can.
I'll be back in my office soon, and then we can talk about it.
Thanks so much.
All right, no worries.
Is it glasses?
Yep,